So my name is Helen He. I work at Lawrence Berkeley National Laboratory at the NERSC Supercomputing Center. And I'm going to talk about process and thread affinity with MPI and OpenMP. This is not specific to climate applications. It's useful for all scientific applications on the current architecture trend, HPC computers. It's very typical that we're using hybrid MPI OpenMP programming model with MPI between nodes and sockets and OpenMP on the node or sockets. So typically, most systems today are non-uniform memory access system. We call them NUMA, and so accessing memory in remote NUMA is much slower than accessing memory in local NUMA. And there's also on-package memory, high bandwidth memory sometimes on the node. And accessing those high bandwidth memory is also faster than the traditional DDR memory. And when it's packet, you can see there's a diagram here, multiple cores. There could be multiple sockets, and each socket can have multiple NUMA domains. And within it, you have multiple cores, and sometimes each core has multiple hyperthreads. Just some terminologies, all these affinity terms. So there's a process affinity and thread affinity. What I mean by process affinity is bind processes to a set of CPUs, mostly for MPI tasks in usually scientific applications. And we want to spread them evenly onto different NUMA domains as possible. And thread affinity is on top of process affinity, then you further bind your threads to the CPUs that are already allocated their parent MPI process, for example, and make sure do not overschedule CPUs for threads. Otherwise, you'll have lots of OS swaps that you're not getting the effect of running your OpenMP threads concurrently. So memory affinity, you want to allocate memory as close as possible. The key point here is to use memory from local NUMA domain as much as possible. Cache locality, also we want to reuse data in cache as much as possible. The goal is also we want to promote OpenMP standard settings for portability, either preferred over vendor-specific settings. So to achieve the correct process, thread, and memory affinity is the basis for getting optimal performance. This is also usually a low-hanging fruit. This is much easier than having to modify your numerical algorithm in your application, for example. But it's also essential that you get best possible performance as a baseline, and also then based on that, you could further optimizations and compare with this performance. So in order to do that, we need to understand the hardware architecture first. There are a few tools to do that. One of them is NUMA-CTL, the flag-H for hardware information. This is a Haswell node example with 32 cores and 2 sockets. This does tell you available 2 nodes. This node is not the compute node, it's actually a NUMA domain. So there are 2 NUMA domains in this example. It tells you how many CPUs and what are CPU numbers that are in this NUMA domain. There's 0 and 1 here, 2 NUMA domains, and the bottom node distance is a relative numbers of accessing memory. So it's 2 NUMA domains, it's a 2x2 matrix, and accessing NUMA domain 0 to NUMA domain 0 or 1 to 1 is faster, and then from 0 to 1 or 1 to 0, NUMA domains are slower in this example. To try to get more information of actually how are these CPUs or how are the system, you want to get more information on system topology and NUMA nodes, the cache information. The tools HWLock LS give you text information, or LS topo gives you graphical representation. Now is that with the same Haswell node, you can see that the graph is not very clear, I'm sorry. So you can see that there are 2 sockets. The top one is the first socket, and bottom is second socket. And within the first socket, you have 16 cores, that's the bottom line. And within each course, you can see 2 numbers here, 0 and 32, which actually that means there are 2 hyperthreads in this first CPU. So based on the information on the previous 2 slides, I actually draw a simpler diagram so it's easier to see. So for this Haswell node, you have 2 NUMA domains 0 and 1, and each one NUMA domain has has 30, each NUMA domain has 16 physical cores from 0 to 15. And then the green numbers are the logical cores for each core. 0 and 32 are 2 logical cores within the core 0 physical. That means actually there are 2 hyperthreads within this physical core. And the memory attached to each of the NUMA domain. These numbers are useful that when later on when you have the affinity information displayed, you want to check back with these numbers to confirm that you're getting the correct affinity. To process MPI process affinity, there are a few options. This is an example with Slurm SRAM options. Similar options exist for MPI round as well. So you can bind your process to threads or cores or sockets, or you can give a specific list of CPU list or a NUMA domain list, map LDOM as well, different ways to make sure you bind your MPI process first. For NUMA CTL, you can fine tune how do you want to handle NUMA. So for example, you can use NUMA CTL and with different options, and then my application executable to replace your real executable. Then you're using the fine-tuned setting of new CPU or memory for your application. Dash CPU node bind 0, 1 example here is you want only use cores of NUMA domain 0 and 1, and dash man bind 1 is using only memory from NUMA domain 1. One example in the KNL, Intel KNL quad flat mode, the high bandwidth memory is the NUMA domain 1. With that, you can make sure you're using only high bandwidth memory for your application. As I mentioned, we wanted to distribute MPI tasks as evenly separate them out onto different NUMA nodes. Here's an example in a few years back on a NERSC XE6 system. There's a one flag as to specify how many MPI tasks per NUMA domain. So this is an example comparing with and without. Without this flag, you're having 4 MPI tasks all onto the first NUMA domain, and then 6 threads per task or be allocated onto this first NUMA domain. Of course, you're idling the other 3, and the performance sucks. From you can see from the plot there, the blue ones are with this flag, and red ones are without. And OpenMP Thread Affinity, there's 3 main concepts: the hardware abstraction to define where are the OpenMP threads can be placed on the hardware, and mapping strategy and OMP proc bind to define how are you going to bind your threads onto these places, and then OpenMP number of threads, how many you want to use. There are environment variables to control those, or clause on the parallel region. I'm going to show a little bit details in the next few slides. OMP places, it can be abstract name with specific list. It can be threads or cores and sockets. So these are placed. Then when you can have a specific list of CPUs, and usually you would set export OMP places equals threads or cores, and then each unit of this thread unit of the hardware will be where you can place OpenMP threads on. And OMP proc bind defines whether you want to bind your threads onto those places. True and false is on and off, and there's are more fine-tuned close, spread, and master introduced in OpenMP 4 that do imply they're also true, but then most commonly used are close and spread options when you bind threads close to the master thread or as far as possible. One of the example, when you nested OpenMP, you would probably want to use spread on outer level and close for the inner level. Next slide, please. Just want to give some illustration of the compare between close and spread. Here's an example with 4 cores and 2 hyperspreads each. When you set OMP close, proc bind equals close, you're going to have all 4 threads onto the first 2 cores and each on each of the hyperthreads. And when you spread them out, you'll use 4 cores and 1 hyperthread each. So consideration of between close and spread. When you spread them out, you're most likely to be able to get more aggregate memory bandwidth, especially if they're on two different on multiple NUMA domains. You'll be using memory bandwidth on both. And for closed, you're getting the advantage of more data locality. So it's a comparison for the test. For the real application, you can do this performance comparison and choose whichever is best for you for the application. As I mentioned, a num thread and procbind you also can use in OMP parallel region as a clause. There's not OMP places clauses yet. Set number of threads, different ways to set that. I just want to mention there are different precedences, and if you do nothing, you get default compiler options, default number of threads based on your hardware and compiler choice. That's number 4. And then if you do something, you do it OMP num threads equals 4. That's number the third choice. You can do it runtime environment setting. Or for more portability, number 2 is you can set num threads API call. That's the number of threads used for the next parallel region. Or for each individual parallel region, you can use a clause. This is takes highest precedence. In the real applications, my suggestion is that you probably, for the easier and runtime because when you use a runtime environment, you do not need to recompile. So that's most convenient OMP num threads, export OMP num threads. And then for certain individual regions, for example, you have a nested OpenMP region, and this is only a small part of your overall application, and you probably want to set num threads or use a clause. Probably use a clause best for the level of control. Then outside of other region without num clause, you would use the OMP num threads environment variable to control the number of threads used. I want to talk about first touch memory for memory affinity. So what it happens is that in this example, you have a number of OpenMP threads for say parallel loop, and then each thread will be responsible for a portion of this those array. And then in order to get your data to be close to where your threads are, if you do a perfect initialization, so first touch initialization, then you will be getting data. You'll be having data local to where you are. This is because this is caused from the first touch policy by most Linux operating system out there. So without first touch, you would do initialize by master threads only, and every local portion of the array will be close to the master threads, mostly on the first NUMA domain, for example. In this example, if I do OMP procbind equals close, that means if I have, say, 32 threads on this, there are a total of 64 logical CPUs on this node. So if I'm using 32 and OMP procbind equals close, they will be on the first NUMA domain. It doesn't affect the memory bandwidth when your thread number is lower than 32. But when it's over 32, without first touch, they are the half of the threads. There will be threads on the remote NUMA domain has to access memory that allocated by the master thread, that you are not getting the performance. So just want to mention quickly force sharing. Make sure you don't do that. It's caused by multiple threads need to update the same cache line, so that the OS has to do the cache coherence. They have to do sync for you in serial. The way to avoid that is to use atomic and critical when you update the same cache line, or use private variables. Procbind choices, close and spread. In this example, again, when you do close, same as shown in my illustration, that when you do close and use 32 total threads only, they'll be all on the same NUMA domain, that you're wasting the other half of the memory bandwidth. So you can see with the OMP proc is closed, you're getting only half of the peak memory bandwidth again. And when you have, but with OMP proc spread, you're already having threads onto multiple on both of the NUMA domains that each one can, so both the memory bandwidth from each NUMA domain can be used. But when you number of threads is over 32, even with closed, there'll be some threads onto the second NUMA domain as well. Then you slowly pick up the memory bandwidth in this example. Nested OpenMP, we can skip the slide. Basically, this is a simple slide, simple code for nested OpenMP. Just want to mention, I did already said something about OMP proc bind is recommended to do spread and close for the nested region, so that the initial thread is one thread, and then when you have the first layer of OpenMP parallel, you spread so that they are out onto different cores as far as possible. But in the next region, you want to be closer to the first level so that you take advantage of data locality. Example here, with the 68 cores on KNL node, we had lots of trouble to initially to get the quickest to get the best affinity. If we do a naive MPI round S round, what we get is, even though we have all these OMP settings nicely, what we get is a mess that you would somehow you would thread 0 for rank 0, thread 1 for rank 1, or on the same physical core. So the reason was that is we didn't do well for the CPU bind, and we didn't do well for to distribute MPI the threads as far as possible. So the ways to do that is, we actually want to waste 4 cores. 68 is not a good even number. With 64 cores, there's a flags -C here for the S run to allocate the number of logical cores per MPI task. So without it, it's tried to giving you 68 times 4 hyperthreads divided by 16 MPI tasks. So your MPI tasks are crossing core boundaries. So with that evenly nice number, and now you're getting 4 cores each for each MPI task, and then also without CPU bind, you're getting all cores allocated on the same core 0. So both are needed, and Intel MPI is very similar in settings, IMPI pin domain to mimic -C16 of the SRAM. With those, now you get very good looking affinity MPI tasks evenly on cores and threads on evenly on the tasks. I'll go really quick. So this is comparison naive and optimal. One of the application we get 33 times flow down without it. Mention a few OpenMP 5 affinity features. And the task to data affinity, you can give a hint to OMP task, that a thread for that task you would want to use a thread that's local to that data that you need. A and B verifications, you can use a binary we give for the nurse people, or we actually want to promote the OMP environment variable, display affinity and affinity format. When you set it to true, you get an automatic display, and you can set custom affinity format, lots of fields here, and you can customize with your own words, host equals something, and format. This is good for integrate MPI tasks, because OpenMP does not know this affinity settings does not MPI. So you could call an API from MPI task 0, for example, and display your affinity with some your custom words there. There's OpenMP memory allocators. So you can choose allocate your memory from where you want, like high bandwidth memory or low latency, for example. A slight example here, you can allocate wherever you want from, and also you can define your own allocator. Some best practices, I think I mentioned lots of them. They are understand hardware information, use CPU bind, places, proc bind, verify your affinity, avoid cross sharing, etc. And this is all I have.